Good day, dear colleagues. My name is Vladyslav Kucher. I'm a PhD student at the Glushkov Institute of Cybernetics of the National Academy of Sciences of Ukraine in Kyiv. I would like to propose to your attention our report, Multi-Level Verification System of Large Language Models in Mathematical Modeling Tasks. LLMs are increasingly used to interpret problems, build mathematical models and generate solver code, but they were not built for this. They optimize for plausible language, not truth, so they hallucinate. They are sensitive to how a problem is phrased, and critically they have no reliable signal for their own uncertainty. In mathematical modeling, error rates grow with the number of variables and abstraction levels, producing rare but very hard to detect mistakes, output that looks structurally plausible but silently violates physical laws or produces non-executable code. Traditional text similarity evaluation can't catch this because exact sciences demand formal validity and numerical precision, not fluent phrasing. That means we need a process-oriented verification, checking every intermediate step, not just the final answer. In previous work, we introduced AIMM, Artificial Intelligence for Mathematical Modeling, a system that automates the full problem-solving workflow, formulation, model construction, numerical method selection, and solving, combining AI with high-performance hybrid multi-core and GPU computing. This work built on AIMM by adding a validation layer to improve the reliability of AI-generated solutions. Our methodology rests on 6 dimensions: solution correctness, meaning the result matches the user's actual intent; contextual and factual fidelity, meaning no silently injected assumptions; reliability under repeated sampling and paraphrasing; uncertainty calibration, meaning the system recognizes its own gaps; abstention quality, meaning it can gracefully decline instead of guessing; and for generated code, functional correctness through sandboxed execution. To operationalize this, we decomposed the entire workflow into 8 normalized artifacts: A0 through A7, the raw input representation, a formal specification, a physical model, a mathematical model, a discrete model, executable software, computational results, and finally a natural language justification for the end user. Each transition is a potential failure boundary, so every boundary gets its own dedicated checks. At every transition, a transformer agent produces the next artifact and validator independently scores it. These scores are aggregated into a weighted composite which then drives one of 4 decisions: approve once quality clears the threshold, retry triggering an automated self-repair loop with the error log sent back to the LLM, intervene escalating borderline cases to a human, or terminate once the retry budget runs out. Given the issues raised, verification criteria were derived. These indicators allow us to assess the effectiveness, adequacy, and feasibility of the model using objective indicators. Some of them are hard gate or mandatory to continue the flow, others are soft score or they contribute to the weighted composite score at the end of the step. The pipeline has 4 verification levels. Level 0 passes raw input into a formal specification. Level 1 translates that into physically and mathematically consistent models, checking conversational laws, dimensional correctness, and mathematical well-posedness. Level 2 converts the continuous model into a discrete numerical representation, checking discretization fidelity, stability, and solver compatibility. Level 3 executes the model and verifies solver correctness, convergence, and consistency with the original specification. And Level 4 generates a natural language explanation, evaluates uncertainty and abstention quality, and makes the final orchestration decision. A supervisory tier of validator agents sits above the generative pipeline, inspecting every artifact and producing error manifests for the repair loop. We implemented this as an asynchronous Python microservice backend using FastAPI as an orchestrating state machine, with validators and transformers running as decoupled services on a shared message broker. They are communicating through a strictly typed schemas, so new domain-specific agents can be added without touching the core. Let us consider a classical electrical engineering problem, determining the branch currents in an electrical circuit without using the ammeter. Since direct measurement is unavailable, the solution is obtained through mathematical modeling. The circuit is first described by Kirchhoff's laws, resulting in the system of equations shown in equation 1. This system is then transformed into its matrix representation in equation 2, which is used by the numerical solver. Although this is a simple example, it contains a common failure point for the large language models. An unverified LLM might silently reinterpret the polarity of the voltage sources, or introduce sign errors during transformation from the physical model to the mathematical representation. The proposed multi-level verification framework prevents such errors by validating physical assumptions before equation generation and by checking sign consistency throughout the entire transformation pipeline. The experimental evaluation was performed using the circuit parameters shown on the slide. The modular microservice prototype successfully resolves such complex mathematical modeling problems autonomously, providing step-by-step auditability and preventing the silent propagation of mathematical errors. To conclude, this work addresses one of key challenges in applying large language models to scientific computing: the absence of guarantees that generated solutions are physically, mathematically, and numerically correct. A multi-level verification framework has been proposed to validate every stage of the mathematical modeling process rather than just the final result. The framework combines specialized validator agents with a deterministic routing mechanism, enabling early detection, localization, and correction of errors before they propagate through the computational pipeline. The case study demonstrated that the proposed approach preserves the consistency of the physical model and produces an auditable and numerically accurate solution. In future work, a unified validation score will be developed, uncertainty-aware verification will be incorporated, and the framework will be integrated into production-grade AI systems for mathematical modeling and scientific computing. Finally, this slide presents our research team. Thank you very much for your attention.